So, so the goal here is, I mean, in DDPM, while training, you want to find the network weight, which is the mu theta, to minimize some kind of like loss. This loss is given as this 1/2 q squared of mu. I want to remind you, this is something we can estimate. So this is the neural network we're trying to approximate. So this is some like weight right here, where this mu of q at t at 0 is something like linear combinations about xt and x0. We did that, I mean, in the last lectures. So this is something like 1 minus alpha t minus 1 bar square root of alpha t divided by 1 minus alpha t bar xt plus 1 minus t square root of alpha t minus 1 minus alpha t. Okay. So this is something we so we did this calculation last time. And we can, I mean, of course you can like design this mu theta like as a some like neural network we try to approximate this point right here, and also and you can sample this xt and immediately and because you can sample everything and from this and a Gaussian distribution example, we have talked about this. I'm going to kind of summarize everything like momentarily.
Sorry, is that a 1 divided by 2 sigma q square?
You mean this one?
Oh, no.
Yeah, sigma q squared. Okay, sigma q is the following. Sigma q squared is the following. 1 minus alpha t, 1 minus square root of minus 1 bar divided by 1 minus alpha t. Okay. So a common trick that we use is we don't design this neural network directly on this one. The common trick is we design this whole thing because we know, and we know xt. So it is designed as like that. 1 minus alpha. So we know all these terms of alpha t bar, all these terms. So this is actually can be treated as a constant, just being the same, but we just don't know at 0. So when we and the key is we're trying to learn this kind of denoiser that can denoise from the xt to x0. So this is actually a neural network. So we're trying to learn a neural network that can denoise from xt to x0. Okay. If we design this kind of thing, my L, I think this can also answer the Josh question. If you really want to denoise an image, you technically just take this xt and you know like how long does it and moved, you can take and take this neural network and it can technically bring back to x0. But this approximation to x0 is very crude. It won't be super accurate. And the way that you see is it's not really actually the denoising if you actually kind of implement that. Because the focus here is actually to generating new images rather than trying to denoise some like noisy images that we already know. All right, so if we design our mu theta this way, then this loss functions can be further simplified to like that, minus alpha t squared 1 minus alpha t bar squared, then which is this denoiser. Like that. Okay, but that is the loss term at t, right? This is a loss term at the time of t. And your t can move from 1 to capital T, right? And that's why you are actually getting, and you need to sum them together, right? So, I mean, if you go back to my elbow, and forget this, like the matching term, the prime matching term, so kind of which is constant. What actually is changing is this follow. So we just copy what we already have. You see it has a two term. I mean, this term actually starting from t and t equal to 2. There's a one like additional term that is at t equal to 1. In fact, you can show this top one right here. I'm not going to do this math, but you have to trust my derivation. This right here is minus of 1 over 2 sigma q squared divided by 1 of x theta and of x1 minus x0. Right? And so we know this whole thing should be very compacted, and like and then is everything start from 2 and then leave out t equal to 1 doesn't make any sense. And we should have a like much more compact version of everything. In fact, if you can define the alpha 0 equal to 1 and the alpha 1 bar is alpha 1, this actually we can combine these two into one. So this actually can combine everything. So I'm not going to rewrite everything. This things can be absorbed from t from 2 to 1. So this is the whole idea right here. If we take this whole thing, this is what be my and the loss functions. and which is my part of my elbow, because for elbow there's one more term which is parametric, but it's a constant. So I mean, if we remove this constant term, this will be the loss we're trying to minimize. Okay, so if we sorry, I think I mean, if I can put a minus sign here, because for elbow we need to maximize it, and for the loss function we need to minimize it. So and a better way to say it, it's star equal to RQ max of elbow, which is a theta, but this is also an RQ B of my elbow. So because I remove this minus sign, then the maximization problem becomes the minimization problems. Okay. So if we actually look into this term right here, so this is actually a denoising problem. It denoise, basically denoise from xt to an x0. So we have a ground truth of x0 here. And you want to train a neural network such that it can map from xt to x0. So this is, and this here is the noise image. And you want this and a ground truth image, and versus the noise and imagery. And also, this xt is not like some random noisy image. It actually has to follow some distributions that we already talked about, and particularly you have to then make sure your xt actually follows this distributions of xt given things. In this case, it's equivalent to say, and we have to sample this xt in a particular way that is square root of t bar x0 plus and square root of 1 over t of this. This epsilon is a standard function. So this is basically the forward sampling, but this is very cheap, and this is only one step in a data generation. You can step from x0 to xt. These are actually the weight for each t. So that means my weight of my loss at different t is different. So it's not like universal and uniform weight. So that means if you want to train this, you can use scheduler to tune your and the weight, or you can tune this learning rate accordingly. But in practice, what people do is they just get rid of this. Okay, there are a lot of people who test this whole thing, and they find out the performance is better if you get rid of this part, which is kind of very disappointing for a mathematician. But in practice, it's cheaper and it works out. So this is sampling part. This is non-uniform part. This is the denoising part. At last, you have to actually sum from 1 to the t. So that's a summation, but you don't need to do summation, right? Because this summation, that means you actually have to do and calculate from 1 to the t, and one by one. And this thing can be replaced by t is sampled uniformly from 1 to t. Because the forward sampling here is so cheap, with only one step, you can randomly throw a dice and pick a random t right here. Then you can calculate this loss functions very, very cheap and very, very quick. Okay, so that's the meaning for each part. But let's just and write a whole and whole you can use that for training DDPM. For one image. So for each image, x0 in this training set, you're going to repeat the following. The first things, take t uniformly. So this uniform is like you pick an integer uniform, right? So for 1 to, I mean, this has to be an integer. Then what you do is you do this forward sampling for one step. So you can calculate this out and alpha t bar very quickly. So it just remind you this alpha t bar is alpha 1 to alpha 2, like multiplications from alpha 1. Is x0 plus square root of 1 minus alpha t or and epsilon. And it is sorry, I think I missed the epsilon is 0, 1. Then you take gradient. So and basically using the backward propagations to calculate the gradient of the weight of x theta t minus x0. Okay, so you just, and this is be trained in SGD versions. Of course, you can make it more complicated for the mini batches if you need. So for the mini batches, that means, I mean, for one specific image, you are not just picking one T. You can pick maybe 5 or 6 different T's. Then you can and sum this and 6 like and different lots together and take the gradients then. Okay, so I mean, this can be done very easy. The common choices in DDPM is you pick T equal to 1000, and alpha T is something like this: square root 1 minus 0, 2 T equals T. Right, so this is actually decays very, very slow. So this is the training. So say like after training, you can find out the best weight of theta and to have this denoising. Then we can do it for inferences. So what is the inference means? So the key for training and the DDPM is we want to train our like weight, which is x theta and x t. So you train this thing right here. The inference means is we want to generate an image. Generate an image out of nowhere and out of something that has never been seen. So this is slightly different from the language of the I would say the statistics, because statistics, if you talk about inference, is actually talking about trainings, but I mean it's and it is like slightly different languages, the variables. So once the x theta is trained, so what you do is we know I can take reversal back from xt to xt minus 1 because we know this actually follows as this. We know everything is a Gaussian. This is a normal diffusion of mu theta of xt with secant mu squared like any. Okay, so basically, if you know the xt, then you can example xt minus 1. Then you put this xt minus 1 right here, then to example xt minus 2. Then gradually you can move from capital T to 1. Okay, so this is the whole idea, but the step is as follows. The first is you start a white noises. So basically, the x capital T is standard white noises. Example, complete standard noises. Then what you do is you repeat this T from T minus 1 until 1. So the first thing is you calculate x theta hat of xt using this trained neural network or trained denoiser. And then what you do is you count an example xt minus 1 according, which is we already know the formula. So this and this epsilon is like a standard Gaussian diffusion. So these are the steps. But the issue we have to go back 1,000 steps from t equal to 1,000 and back to and like t equal to 0. So now you can think about everything is like that. So I have layers, some neural network. So this is my x of 1, which is one image. And passing through this neural network, it can predict x theta of x1, and which is the noise of x1. During training, we can calculate this training loss. And you can do this all the time. T. So this is all the same neural network. Okay. So the input will xt and also the time t. So and then the input is time xt and also time t here. I mean this is 1 here. So basically you need to tell the neural network which time we are heading and right here. So this is very important. Otherwise, it won't train well. So this is the denoise of xt. And actually similar, you have something like this. So until you have xt. So this is the training. So you use the same network for all noise level, but you have to tell and then this like network and which time we are with. But that's the training part. In the inference, actually we have x of t. Then we go back to xt minus 1, go to the xt until we get into x1 and x0. So you do step by step by doing this process. And for each of this, you are going to apply this neural network with a t-1 here. It will actually give you this rough denoiser. And for this one as well, same neural network, it will give you very rough denoiser. But the whole idea is you are going to combine this and this. So here is the trick. People like in deep learning like to draw this kind of diagram. So you do some linear combination of xt and the denoiser of xt plus some epsilon with a zero identity. This will be the predictions of xt minus 1. Okay, so this is kind of like autoregressive. But so you have information from and the data from pure noise, then step by step through this kind of like and a little bit like an autoregressive way, and to do this denoising and one by one. So one question is, I have been puzzled for a very long time, is why not just take this as my x0? Because I mean this is a denoiser, right? So this actually approximates the x0. So you can have this like pure noise and plugging this denoiser, train the neural network, plugging t equal to 1000. It should give me an x0. If you actually increment, then you will find out that's not the case. Yes, this is a denoiser. It can try to denoise, but that doesn't mean it will be close to x0 at all if your input image is completely noisy. So what I mean this actually do is they're trying to make some predictions, very rough predictions, then gradually correct them by themselves. As t getting smaller and smaller, this denoiser is doing better and a better job. If t is really, really large, this denoiser is still giving you like garbage. It's still very noisy, and the result doesn't make any sense. Hypothetically, this will be close to x0, but when t is very large, this is not close to 0 or approximately 0. And things are very far away from x. So that's why you cannot just plug in this like into your neural network and expect to get an x0 at all. All right, so this is basically the training and inferences for DDBM. And this is how, and if you want to implement that, and you can do it. But I want to step back to look at the DDPM for a little bit longer time. Why we want to do this? So the reason is very simple. Everything is discrete, right? So you do this step by step from t from 1000 to t to 999 and keep going on to t. And of course, the issue is if we have this 1000 t with 1000, that's like 1000 steps we need to process. That's really, really expensive. Okay? And although it can get a very good quality and get some like generate some image with very good quality, but you don't want to wait it forever. So that's why some math need to be taken into account here. So right here, I mean, this is still like very computer science, but I'm just a little bit like in few minutes you will see how the math comes out. And I want to remind you the first lecture that we did on stochastic differential equation. This is almost the fourth lecture. We haven't talked anything about the stochastic differential equation. So this is the first time I'm going to do the connections from DDPM into stochastic differential equations. So I'm going to erase everything here. This is not needed. This is DDPM to some SD. This is something getting really interesting. Once we have an SDE, there will be more tools can be used. So this is why the power of the probability and the stochastic process shows up. So I want to remind you the DDPM, the whole process is, I'm going to write this way. Square root of 1 minus beta t, xt minus 1, plus square root of beta t, epsilon beta. So, and you can use alpha. I mean, if you want. I mean, that would be square root of t, this will be square root of 1 minus alpha. And it doesn't matter. Okay, so we know this is discrete. I'm going to turn in this discrete scheme into stochastic differential equation. So that means I need to define something. Define beta t equal to, I want to say beta t, I mean, it's a continuous function times delta t. Okay, so this is not very formal, but you know what I'm talking. And also my delta t, I'm going to define this as 1 over here. Okay, so you can think about this iterative scheme is some kind of there will be some underlying and continuous differential equations, right? So I want to use this discrete iterative form going back to get my continuous forms. So then my xt here, so I'm going to switch one delta t here. So I mean, and because I want to have this xt and minus 1 here. So this is slightly off by most standard textbook, but we know what I'm talking about. Just like shift by and a delta t. Okay, if we plug in this is xt plus delta t. This is 1 minus beta t plus delta t of this delta t times xt plus square root of beta t plus delta t times delta t. Same thing, epsilon t. Okay, so this is nothing but we just define everything, plugging back, and assume there will be some underlying and continuous functions of x and of xt. Okay, so then you are going to use, I mean, this is quite complicated here. So, and I'm going to and expand this out. So we know 1 plus 1. Okay, so this is something that we know in Tate expansion. In most of things in mathematics, if it is small, we can do some Tate expansions. So this is approximate 1 over square root of 1. I believe is 1. Sorry. This is equal to so this is by Tate expansion. This is 1 minus all half beta. Okay, so we are going to use this thing right here. So then this xt plus delta t is approximately equal to 1 minus beta t plus delta t of delta t divided by 2 is 1 minus and xt plus square root of beta t plus delta t right? So you move one of xt to the left hand side and divide by delta t. All right, so if you move one of the delta t, and xt here, so this will be like that, and you divide by delta t. So delta t, this cancels out. This you have to be careful because this is a kind of random noise. You cannot just divide it by and a delta t because this whole thing is scale with an order of square root and square root of delta. So this is actually just you can only divide it by and square root of delta t. All right, so if you do this and take the limit, let the delta t goes to 0, you are getting a stochastic differential equation. So this is dxt equal to minus beta t divided by 2 xt dt plus square root of beta t dwt. So this XDE is something has a name called non-autonomous. Constant Uhlenbeck process. So why this is non-autonomous? Well, the most part that you encounter is your right-hand side doesn't depend on t explicitly. In this case, the right-hand side is, and it depends on the term of t explicitly. So that's why it's non-autonomous. This OU process, Olmsted-Uhlenbeck process, says the drifter right here is only linearly depends on the xt. The diffusion doesn't depend on the xft right here. So this is what we and something called an Olmsted-Uhlenbeck process. It's a very, very famous process. But in generative AI, there's a name covariance preserving SDE. So why this is called, covariance preserving SDE? You will see that later on. But honestly speaking, this kind of like process is not the mainstream in the stochastic process. If you ask people who work on stochastic process, people like to work with linear system, but linear but more like autonomous. So that means this right-hand side right here doesn't depend on the time explicit. So that will be much easier to be handled. Something that, and it depends on that, that would be pretty hard to do. Sometimes it's even a question whether the stationary distributions exist or not. But nevertheless, in the first lecture, we learned something called reverse diffusion equations. So that means we have a forward process. That means we know the x0, that the forward process can go from x0 to xt. There will be another reverse diffusion equations. This reverse if you go back to my first lecture, the reversed diffusion equation is as follows. I said it before, maybe in 10 years, this whole equation is meaningless because there's no way we know this quantity right here. But nowadays, if something is not known, we can always approximate by neural network. So this is the philosophy. And what does this reverse diffusion equation means? In discrete form, that means if we know xt, we can sample xt minus 1, sample xt minus 2, until we can sample xt. So that means we can actually going back from xt back to x0. So that means what? And this numerical scheme says xt plus and because we have to go through the minus sign, so that will be minus t right here. So everything minus becomes plus right here. Plus gradient x of log of p px plus square root of beta t delta t and epsilon. So this is basically the discrete form right here. And of course, that's you can combine them together and to make it things and easier to understand. But this is, and I want to remind you here, we did one approximation here, right? We can put this approximation back. This will be roughly approximate. Is 1 over square root of 1 minus beta t. Yeah, I think yeah. Of xt plus beta t divided by 2 gradient of x log of p t of xt plus and square root of beta t. So this is basically the scheme. So we come up with the new scheme right here. If we can approximate this things well, then we can move from x capital T back to xt minus 1, xt minus 2, and so on. So this whole thing, you would think, okay, so this is replaced by, so I'm going to call this using a neural network called S theta of xt, which is a neural network trying to approximate this quantity. If we can approximate this quantity by neural network of this S theta xt, then we can go through this process very quick. And because everything is like SDE, there are a lot of tools that can speed and it can speed up this and reverse diffusion and equations. But the tricky thing is, what is this? So what's this? Right. So I mean, that's not that that easy here. And how do we get this part? Okay, so now the question is, how can we calculate this? So I will just briefly mention a little bit, maybe in today's lecture. In the next lecture, we are going to finish why this whole thing is very. So like right here, this give you the, and I hope this gives you some like enough motivations. If we can approximate this term by neural network of this one, then we can go back from x2 to x0. Very easy. So there's no more forward sampling. All we need to do is you start with just a white noise, run this SDEs, then you should be done. So this will be significant faster than training and the inferences, particularly inferences on the DDPM, because in DDPM we have to run 1,000 steps, but here this is an SDE. There are multiple ways in SDE that we can speed up this and the simulations. So we can take advantage a lot of any new stuff. But now the question is, what is this, right? So, all right. So let's just give it a try. So here, what we want is probability of xt. Right? We know this is integration of this whole thing of x0 and dx. So this is nothing but a conditional probability. So we can write up everything in terms of integrations, and also we can write everything in terms of expectations. So this is probability of xt. All right. So we know this one. So this is a Gaussian, or some sort of Gaussian. So we know this part. And also Px0 is given. So sorry, I mean, so x0 is given. Because that's all by training data set. But we don't know probability of x0 precisely. So this is what we don't know yet. But we can do something to approximate Px of t. Okay, so, okay, that's good. So, and this is something we already know. What we really want to know is gradient of xt of log of P of xt. Right, so let's plug in to this gradient of xt log of expectation of x0 sample from x P of x0 P of xt condition x0. So the trick, so we know this is the log and the gradient and the logarithm and of these things is gradient of xt and divided by this. And of course, when engineer, we can swap the order of the derivative. Okay, so let me put this derivative inside. We swap order. Okay, the philosophy, general philosophy is always we swap order first to see whether it can work. If it cannot work, that means it might be a problem. If it can work, just let it work. It's likely, it can work. All right, so you swap order of the and integrations and the derivatives. So that means that I have a two expectation right here. I have two quantities we already know. So what we can do right here is we can sample. So we can propose an estimator. This is approximated by integration of, the example from S samples of gradient of xt, probability of xt. We know this is a Gaussian, so this is something, and we already know that. And this is summation. This will be S of I. So example, all these like n x0 right here. So this will be xt 0. Right? So you're just using these things to sample that out. Okay, so if that's the cases, and what you can do is, this is just example for fix of t, right? So this, t is fixed. So then what you can do is you can propose your loss function is equal to, you also need to work on xt, right? So you need to sample xt of xt here. You do this estimator, an estimator. Right? Calculate algorithm of this whole thing. Subtract s theta. Xt. And you train this. It's a very, very reasonable. You expect it to work. Unfortunately, it won't work. If you actually check the Song Yang's paper, they didn't use this method. This is the most intuitive way to work. Right? So, but why did it do that? All right, so here is the reason. Okay, so sometimes I really hate to read like those deep learning papers because they don't present things in an intuitive way. They don't, I'm explaining these things one thing. It took like maybe like 3 more people trying to figure out what's going on there, find out the reasons. The reason is following. This S, okay, so if you choose S really large, it can work. This only work when S is really large. But in the most of cases, when we do, practice, the S that we can choose is mini batches. This mini batch is pretty small. We cannot make a very large estimations. This estimator is a biased estimate. Is a biased estimate. So this is called a ratio estimate. So basically, both of this, the denominator and the numerator is an expectation. One and divided to another. If you use, and each of this, you can just sample that and without any problem and without any biases. But if you using this sample mean and this is another sample mean, then you divide them together. This is a bias test. It took people a little while to realize to using this is a bad idea. This only work. I mean, the bias is order of 1 over s. Right. So if you choose s really large, thousands, I mean, can work. But in mini batches, nobody used s to be thousands, just maybe 16 or like 8.
So the S here is a batch size?
It's batch size, like mini batch size. Yeah. Then this is bad. I mean, if you, I mean, don't know why this is biased. You can like, and Wikipedia, like what is the ratio estimator? So I mean, this is what I'm talking right here. So if this gradient is biased, of course, this training will be bad. You won't, I mean, it won't work. So that's why previously when people work on all these kind of problems using this one, they stop here. I mean, it's very natural, right? I mean, it's very natural, but won't work. So that's why we have to rewrite things in a different way. So this is the novelty from Song Yang's paper. It's quite technical, but somehow it just worked. The key motivation here is we need to write this quantity in a different way. So okay, so right here we're still using the same and the same argument. So this will be gradient of xt, t of xt divided by xt. Here we haven't used anything with respect to x0. So then I mean, so the difference is here is right here we have used this and a conditional property right away for p of xt. But here we just calculate the gradient first, then we use this and a conditional property. This is dx0 divided by xt. All right, so then I'm going to do one more trick. This one more trick is I'm going to multiply an xt conditional x0 and divided by the same thing. What's this? This is nothing but gradient of logarithm. Right, so this is clear. That's good. And then we are going to move this back. So this is becomes this integration back p of xt. This is p of xt. If you look this closely, this is nothing but base root. So and you can basically flip this to x0 given of xt and a gradient xt log of p xt 0 dx0. All right, so to write this out, this is basically says expectation of x0 follows of x0 conditional of xt. Gradient of xt log of p xt conditional of x0. Okay, so going through all this derivation, then then what you do? This you also need to like sample for and for the xt as well. So basically you sample the x0 following this way. So you basically need to sample pair of x0 and xt. So so what you do is you are going to get this loss function. Loss function is here. I'm going to write out the loss. That will be the end of today. The loss we proposed is gradient of xt of logarithm of p of xt x0 minus s theta xt of p. Right here, so you actually need to sample x0 and xt. Then x0 actually follows probably of x0 and xt samples xt. So that is not exactly this one, right? But I don't have time to talk about why this is actually same. Is this one. These two are equal. And we have this analytical result right here, so that will be great. Just for training. And the most important part, this is unbiased. Unlike the one that we use right here, this one actually is unbiased. We didn't have the term that one divided by another. And then we can use small batch size. That S to be 4, S to be 8, and that will be fine. If you choose S to be 4 to be 8 in this cases, you'll be screwed. But this is the first key innovation coming from the paper. And the paper is very technical. But if you go out everything else, that's the motivation. That is the loss functions. The key and the key loss functions, which is in the next lecture, I'm going to show these two are equivalent mathematically. Okay, but provided you have infinite of S, like if S goes infinity, these two things are actually the same thing. But if you only have a finite S, this right here, and it doesn't have any bias. This one over there has bias. So that's why this work, this failed. All right, that will be it. I will be continuing these things on the lecture 5. If not finished, I might have one more lecture to finish that. But I hope I can finish at least for one more lectures. All right, that's it.
Green said thank you.
Any questions? Yeah.
Are these two methods like before or after
implicit score matching?
So implicit score match, that was after implicit and score match. I skipped the implicit score and score matching, but I will recover that on the like Friday's lecture. Hope I can get that. As I'm going to present a unified version of everything. So basically, you can plug in your choices, and one choices will be unified, one an implicit version, and one choice will be EDPM. So that would be like very nice way to include everything. So that's the power of mathematics. Mathematics is we're trying to bring a like general framework and everything just to fill in the blanks. Yeah.
If one is biased, the other is unbiased, in what sense are they equal? What do you mean by that?
One S is large, then it will work, and these two things will be kind of close to each other. Yeah, yes, as a conjugate.
I don't know that.
Yeah.
I guess you can't. It would be unwise to do a Taylor expansion of log to maybe get a unbiased estimate.
Yes, but then you need to know the distribution precisely right here. That will be quite expensive. And also you need the variances, like all these informations. All right, but I will be much cheaper to work out this way. So. Okay.
Okay. Great.
All right. That's it.